Any question from last time? Let's start with a bit of a small review. So last time we started on this chapter 1.5, and 1.5 is about elementary matrices. So the idea itself of elementary matrix is not too hard. I think it's about here. Okay. So elementary matrices, they are basically writing the elementary row operation into matrix form. Okay. And so there were 3 elementary row operations. So we also have 3 elementary matrices. And the first type is this interchange of 2 rows. So you have those interchange matrices. I guess I should go back a little bit. So elementary matrices are obtained by performing the elementary row operation on the identity matrix I. Okay? And so we have row exchange. So here is the example of exchanging the first 2 rows and multiplying a number on a row. So here is the elementary matrix for multiplying 3 on the 3rd row. And then we have adding a multiple of a row to another row. So here is an example of adding a multiple of a row to another row. And so if you apply an elementary matrix on another matrix, then you will on the left, then you will do that row operation on that matrix. So now we can write the row operation as matrices. That's a big part of chapter 1.5. Okay? And also there are inverses to every elementary matrix because every row operation has an inverse. Okay? And also we say 2 matrices are row equivalent. So basically it means that they're corresponding to it's a little different. Anyway, they are row equivalent if you can do row operation to get one matrix to another matrix. And you can write that in terms of elementary matrix. Means that there is a string of elementary matrix. You can multiply on one of them to make it into to make one matrix into another matrix. Okay, so row equivalent. And and now we go to first bit of linear algebra theory. Okay. And this is a theorem about what the matrices are not singular. Okay, so we prove that there are 3 equivalent conditions. First is that the matrix is non-singular, which means that A minus 1 exists. And then the second condition says that if A is non-singular, then Ax equal to 0 only have the trivial solution 0. Remember that this is a homogeneous system. And it's easy to see that a homogeneous system always has the trivial solution because if x is 0, then the 0 vector multiplied by any matrix is still a 0 vector. And anyway, if A is non-singular, then x equals 0 only have the trivial solution. And this is easy to see. This is one of the things we'll do a lot is if A is non-singular, then we can cancel A by just multiplying A minus 1. Okay, so that's exactly what we do. We multiply A minus 1 on both sides of the equation, then we see that the left-hand side becomes x, and the right-hand side becomes 0, so we have x equal to 0. Okay. And then the third one is that A is row equivalent to identity. Okay. And we also have a proof for this, so we have this whole 3-way around. Okay. And so A is row equivalent to identity, and this is also and B2C is a bit harder, and but we can see that C2A is a bit easier. So if A and I are row equivalent, then they are a set of elementary matrix that you want A to make it into identity, and the sequence of product of those matrices is exactly A minus 1. Because we know A minus 1 times A equals to identity. Okay. And that's theorem 1.5.2. Any question? Okay. And so here a bit of example. So if A is non-singular, then yeah, if A is non-singular, then then A is equal to 0 only have a trivial solution, and A is the row equivalent to identity. This is our statement, and we also have that if these three are all equivalent, then the negation of all three are equivalent. So A is singular, and zero non-trivial solution, and A is not row equivalent to identity. And here we have an example of A being singular. Okay, so if A is the singular matrix that we say is singular before, A equal to this 1, 0, 0, 0, then we have that A times A times 0, 1 equal to 0, 0. So this is the negation of the first expression. A is singular, and this is a negation of the second expression. So A multiply on this non-zero matrix, non-zero vector x equal to the 0 vector. So here is A is equal to 0, having non-trivial x. And then the third one we don't have quite a proof, but you can check that. I guess you can try yourself and see that no matter what row operation you do. I guess here we have a proof. The third one we need to say A is not row equivalent to identity, and this can be seen by the last column. Okay, so this column here is 0, 0. So no matter what the row operation you do on A, then the last column will be 0, because row operation only make a column a linear combination of those elements, and yeah, so you can never make a 1 out of those just row operations. Okay, so that's a bit more on theorem 1.5.2. Then we have this corollary 1.5.3 says that so we use this theorem back to our linear system of equations, and now we can have a condition on when do we have a unique solution. Remember we say that linear system has 3 possible solution set. It can either has no solution, 1 solution, or infinitely many solutions. And here we give a condition about unique solution. Okay? So A is equal to B has a unique solution if only if A is non-singular. Okay? And this is related to the theorem 1.5.2 because being non-singular is like a condition A, and and this A is equal to B has a unique solution is very similar to A is equal to 0, only have a trivial solution. Okay? And indeed we can use a bit of 1.5.2 to prove this theorem. So the reverse direction is just like how we prove A to B in 1.5.2. We multiply A minus 1 on both sides, then we get x equal to A minus 1b. And it has a unique solution. And then the back way, we need to do, we use 1.5.2 a little bit. Actually, the negation of 1.5.2 with not A go to not B, we say that we have a proof of contradiction. If A is singular, then A is equal to 0 has a non-trivial solution Z. And solution Z, we can find another solution for X equal to B. So we show that x plus Z is another solution to A is equal to B. And this cannot happen because A is equal to B is has a unique solution. So that's a contradiction, and A must be singular. Okay, any question? This is small review of so this gives us the relationship between singular matrix and having unique solution. And I guess from this corollary, you kind of see that the most important two expression is the first two. A is singular, A is non-singular, then A is equal to 0, only have 1 solution. And that can generalize to corollary, where A is non-singular, then A is equal to B, only has a solution for any B. So in 1.5.2, this was 0 here, and then we generalize this to any B here. Okay, so yeah, so this is the theorem for theorem for the condition for a unique solution. Okay? And now we go to more about a minus 1. Okay? And so if A is non-singular, by definition it has a minus 1. And now we use 1.5.2 again. So from 1.5.2 we say that so 1.5.2, and this is the expression A. So A is non-singular, and then we have expression B. A is row equivalent to identity. Okay, and so if A is row equivalent to identity, as before we said that there are elementary matrices to turn to turn A equal to identity. Okay, and we work on this a little bit, and so we know this EK to E1 are A minus 1, but now we do interesting expression. So we multiply A minus 1 on both sides, and we see that this thing multiply on identity equal to A minus 1. Okay, and this is anyway, this is a bit trivial, but we want this expression because we want a different interpretation here. So we multiply. So we already know those are A minus 1. And we multiply an HR identity here because we want to interpret this left-hand side as doing row operation on identity. Okay, remember you multiply an elementary matrix on identity matrix is applying row operation on it's a row operation on identity because any matrix get multiplied by elementary matrix is doing elementary row operation. Okay, and so why do we want this? We have that if we do a whole bunch of we have that if we do the row operation that turn A equal to identity, then that will turn identity into A minus 1. Okay, and then this gives us the method to calculate the A minus 1 is that you just do row operation on this augmenting matrix. Now this is a different augmenting matrix than we have for the linear system. So we have, I guess I should mark this loader. Okay. So now we define a different augmented matrix. That is, we have a matrix that is have a left block being A and the right block being identity. So this augmenting matrix, if we do the elementary row operation to turn A equal to identity, then we'll turn identity equal to A minus 1. This is because so on the left hand side we'll apply this thing, and on the right hand side we'll also apply these things. And so on the very left hand side we'll turn A equal to identity, and on the right hand side we'll turn identity equal to A minus 1. Okay, and so this gives us a way to compute A minus 1 with row operation on this augmenting matrix that has a block of A on the left hand side and a block of identity on the right hand side. And as we say, we want to use the row operation to turn it into this identity and A minus 1 matrix. Okay, so let's do exactly that. So we start turning A equal to reduced row echelon form. We have the pivot row, and we make the two other row equal to 0 here. And you see that we'll also do something on the identity matrix here. So we add 1 time here, so this 1 add to this 1 here, and we add minus 2 time here, and we get minus 2 here. Okay. And so then we skip all the middle steps. So then you should eliminate this and make all those 1, and eliminate 2, eliminate 1, eliminate this 1, and in the end you will get A minus 1 equal to this matrix. Okay, so that's the idea about using row operation to calculate your A minus 1. And also from A minus 1 we can go back to solving linear system. So we know that A is equal to B, then if A minus 1 exists, then X equal to A minus 1B. You can multiply A minus 1 on both sides. And so this gives us A I guess it's a bit of a detour way to calculate A-1, because if you start with Ax equal to B and do row operation to make this side identity, then you already make this A-1B. But now we separate two steps, so we first get the A-1, then multiply A-1 on B, then we can get your X. So X is A-1 on B, then it's this 4 minus 8 over 3 vector. Okay, any question? If not, then we can go to mode definition. So we have a mode definition about some form of matrices. Okay, so for n by n matrix we define 3 different notation. So first we can define upper triangular matrix. So upper triangular matrix is a matrix where elements are on this upper triangular. Okay, and in terms of definition, we define this in terms of the where are the location of the 0 part. So it means that everything out of this upper triangular should be 0. So it means that for Aij with I greater or equal to j, means that they are on lower triangle is 0. And similarly, we define this lower triangular matrix. Okay, so it means that the non-zero part are on this lower triangular, and it means that the upper triangular should be 0. So for I less than or equal to j, Aij equals 0. So these 3 elements are 0. This is 1, 2, this is 1, 3, and this is 2, 3. You see those for I smaller than j element, Aij equals. And and with the matrix is triangular, if it's either upper triangular or lower triangular, should be intuitive. Okay, and then we also have diagonal, means that the only non-zero elements are on this diagonal. Okay, so on this diagonal is it can be non-zero, and that means that either upper triangle or either this triangle part or this triangle part is 0. So Ij equals 0 wherever I not equal to j. And obviously diagonal matrix is both upper triangular and lower triangular. Okay, and so this is kind of a side note. This is not quite related to the elementary matrices, but we like those definitions, so we put them here. Okay, and so here are the checklists for this section. So the big part about this section is we have 3 types of elementary matrices that corresponding to elementary row operations. Okay, and so their definitions that is just how you get the elementary matrix is you just apply the corresponding row operation on identity matrix. And then we have elementaries. Matrices are invertible, and I guess we should also have another another thing. Okay, so if we apply elementaries, we have some E on A equal to row operation on A. Okay. So if you apply elementary matrix on the left-hand side of matrix, then that is equivalent to you doing the row operation on your matrix. Okay. And then we can define row equivalence between 2 matrices. And actually we can define this before, but anyway, now we see that row equivalence means that there is a sequence of elementary matrix that you can multiply on your matrix to turn from your matrix A to matrix B. Okay, and then we have this 1.5.2 that have equivalent conditions for non-singularity, and 3 conditions. If A is non-singular, means that A-1 exists, and then that's equivalent to A is equal to 0, only have a trivial solution, or A is equal to B, has only one solution. Okay. This is also no. So X equal to B, unique solution. Unique so. And also A is row equivalent to identity. And the next part we start going those 3 definitions that are not quite related to the previous part, but we define upper triangular, lower triangular, and the diagonal matrices. Okay, and yeah, let's try to speed up and let's go to next section. Next section is about matrix multiplication. And I guess this is not really related to a linear system, but it's a nice property about matrix multiplication is that I guess you can kind of do things in parts. Okay? So if you have a matrix, you can just divide the matrix into different blocks as you wish. You have this huge block of matrix, and you can divide it into some matrices. Okay? And say you have this division here, and then you can divide your C matrix into some matrix C11, C12, C21, C22. Okay? Or for example, you can divide your B matrix into 3 parts. So this B1, B2, B3, and here this division is something already do before. You divide B matrix into these column vectors. So column vectors can be viewed as matrices, and yeah, so you can also divide B into B1, B2, B3. Okay, and then this section really just say that if what happens if you divide 2 matrices both into blocks, and then you can sometimes you can multiply the 2 matrices as you may multiply block by block. And for example, we already have example before. So we have that if you have A times B, and if you partition B into columns, then we see that the result is that you multiply A with each column, and those columns together as your new matrix. Okay. And we can actually generalize this into any partition. And the rule is that, so remember that you have A times B, then A and B need to have matching dimension, right? I mean, if A is M times N and B is N times R, then we need to have this N equal to this N, okay? And then in terms of partition, we can also, so there are 4 things to partition, so we can partition this thing, this thing, and this thing. And the important part is that when you do partition, then you need to have matching partition on this N part. So means partition on the columns of A and partition on the rows of B need to match. And okay, so okay, and for example, we have I guess I should have an actual number here. But for example, we have A equal to this matrix, with some B, then we can have AB1 equal to this vector, AB2 equal to this vector, and AB3 equal to this vector, and we have A multiply. So we have 3 different B. Sorry, I got confused myself. So we have A equal to this vector, and we have 3 column vectors of B being the 3-dimensional vector, and we have AB1 this, AB2 this, AB3 this, and yeah, and A multiply on this matrix of those 3 column vector will be those 3 column vector together. Okay, and yeah, also if we have a B being identity matrix, then we have that the columns of A multiply on each standard vector. This E1 to En. Okay, and then for example, we can put there are more examples. So we have A and B here. So we see have a matching dimension in the middle, and now we can partition the row of A kind of arbitrarily. So if we partition the row of A, then we have that the first row times the B will become a row. So this row and this row will do a linear combination of those 2 rows and become a row. So first row of A times B become a row, and the second row of A multiplied on B become another row. Then third row of A multiplied on B get the third row, and A times B is just you listing those 3 rows together to become a matrix. Okay, and I think really this section can be just represented by this slide, and we have a schematic here that hopefully you understand. Okay, so we have A is an n by n matrix, and B is the n by r matrix, and we say we need to partition the n part. So this partition and this partition need to match, and we can do whatever combination of n and the partition, and we will get the n by r matrix. So just like before, we have n by r, and then we have the partition on n, just like this partition on n, and this partition on r, just like this partition on r. So we already have two of this example. So in this column of B example, we just do partition on R. So we say we partition R to the max. So partition R into individual columns. Then in the AB result, we also have a partition of R into individual columns. And similarly, in this example, we partition M into individual rows. And in the result, we will also have the rows partition, so the rows of AB partition into individual rows. Okay, and yeah, so we see more example. So now this is a more abstract example. So we say we can partition B on its row dimension, so like on its columns, and partition B into some B1, B2, and then AB1, B2 will be AB1 and AB2. And I guess now here are generalizations. So before we only have those particular row and column vectors, but now those B1, B2 are actually matrices. And this AB1 and AB2, those are calculated as a matrix multiplication. So you have A multiplied on this block matrix B1, and A multiplied on block matrix B2. And if you list those two blocks together, this will be same as A times B. And similarly, you can partition A in row dimension. So you have A1B times A1, A2 on B. Then you have A1B and A2B, and you can calculate this. Here is a little bit of proof where you partition everything into columns, and so into individual rows, and group them together. And then anyway, you see that this block multiplication, you will give you A1B and A2B, those two blocks. Okay. These two are calculated by just matrix multiplication. Okay, and say you can have another case where you divide the middle part, so A1 and A2, and B1 and B2, and where you divide A in the column, B into row, and so this A1 dimension and the B1 dimension need to match, and that's exactly what happens. So we have those A's here. So that's the number of columns of A1 matching the column number of rows of B1. So both A's here, and also this n minus S and n minus 1 S match. And when that happens, then you see that AB is those two block elements multiplying those two block elements, and you can just think the block element kind of like elements. So you just have A1, B1 plus A2, B2 as your result. And then you resolve A1, B1 as a matrix multiplication, and A2, B2 as a matrix multiplication. Okay. And then finally we can have even more partitions. So we have A equal to these 4 blocks, B into these 4 blocks, and then AB will be I guess we skip the middle derivation, and in the result we just have this 4x4 and this 4x4. The result will be also a 4x4 block, and you resolve each block as a matrix multiplication. So like this block is so let's highlight this. So like this block is so this is actually one block matrix, although there are a lot of expression. It's a whole block multiply on this column block. So you have A11 multiply on B11 and A12 multiply on B12, and adding them together, etc. Okay, and you can do this in more general. So you have A as blocks and B as blocks, then as and this column partition and this row partition match. Then you can write C equal to AB as also a block matrix, where the Cij is this just like usual matrix multiplication, where each element is a number. So you have this Aik, Bkj, and summing over k from 1 to something. Okay. So yeah, that's block multiplication. Okay, so then we have a whole bunch of example. We have A equal to this, then we partition B into blocks. And we also partition A equal to blocks, then we can have this block multiplication. You can see each block can have a different dimension, and the only requirement is those 2 dimensions. So these 2 dimensions should match these 2 dimensions. Okay, and yeah, you see that the partition on the rows of the result is same as partition on rows of A, and the partition on column is same as partition on column here. Okay, so yeah, and then we can have a different partition on A, and we can partition the rows differently, then the result will have a different partition on rows. Okay, and then something a bit more interesting is I guess a bit of application of this is if you have a matrix that's so-called block diagonal. So if you can partition into blocks where some of the so you partition into the 4 block, and this 1 2 block and this 2 1 block are 0. Okay, and when that happens, then we can say something more. So we can say that A is non-singular if only if A11 and A22 are non-singular. Okay, and here is a quick proof: is if both of them are non-singular, then we can write A-1 as also this block diagonal matrix. Okay, so so A is this A11 block and A22 block, and if you just put the A11 minus 1 and the A22 minus 1 here, and you multiply together, then by the block multiplication rule, will be A11 minus 1 times A11, then it will be identity, and this block will be A22 minus 1 times A22, and it will be also identity. And then you look at this whole matrix, you see that you have this block of identity here, block of identity here, then it's actually block of then it's actually the whole identity matrix with dimension n. Okay, and yeah, and also you can check that this is also the right inverse. Okay, so if A is non-singular, yeah, and so if A11 and A22 is non-singular, then you can find A minus 1 as this matrix. Okay, then also if A is non-singular, then we can say then there is some B equal to A minus 1, and we assume B has this block diagonal, and we also partition B into this block form, then BA equal to identity, so we have that. So now we do block multiplication. We have B11, B21, B12, B22 multiply on the blocks, and it should equal to identity. And then the actual multiplication, so this one will be this so we do actual multiplication here. Okay, so this element will be B11 multiply on A11, and then those two multiply and become 0. And this element will be this element is this multiply on A22, etc. So I have all those things. Okay, and then from this being identity, we see that B11 A11 equal to identity, and this equal to identity, and this equal to identity, and then we see that B11 is the inverse of A11, and B22 is the inverse of A22, and so A11 and A22 both. Okay, and yeah, so if you have a block diagonal matrix, then you can find its inverse a little easier, because you can just find the inverse of each individual element separately. Okay, and yeah, so this is about this chapter, this section. So here is the checklist. So block matrix multiplication, just like ordinary matrix multiplication, and so you can have this, say you have a 4x4 block, and then just multiply each block together, and add them together like each block is a scalar. Okay, and but remember that when we want to have this kind of block multiplication rule, then we need to have a matching dimension. Means that the partition on this dimension and the partition on this dimension need to match, like here. Okay, and yeah, let's if we are okay, then let's try to go a little more and go to chapter 2. Okay, chapter 2, and let's see if this works. Chapter 2, and okay, working. And so chapter 2 is about determinant. Okay, I think you should also learn this in high school, but we will be going into more detail than what you learn in high school. Okay, so now we want to calculate the determinant of matrix. It's a very nice thing, and I guess big motivation for calculating determinant is that the determinant will tell us whether the matrix is non-singular. But later on, we see that determinant has more property that we like. And okay, so what's a determinant? We express there are several notation we do on it. So first is we just write as dot of this matrix A, and the determinant is a number. Okay, so delta A is a scalar, is if A is a real matrix, it will be a real number. If A is a complex matrix, it will be a complex number. Okay, and how it helps tell us the matrix is singular or not is this theorem that we don't prove here is determinant A equal to 0 if only if A is singular. Okay, and then we also have a special notation for expressing determinant. So if A is say this 3, 4, 2, 1, then we write determinant as this notation that's just two straight line and these elements of A inside. So 3, 4, 2, 1, and the two straight line is a determinant. And yeah, as we say, determinant of A equal to 0 if only if A is singular. And here is an example of calculate the determinant of A of this 2x2 element. Okay. And how we calculate determinant for 2x2 matrix is, I think you do this a lot in high school, is you kind of connect those two lines. So you multiply together this diagonal, then and multiply together this off diagonal, and subtract that. Okay? So determinant of A here is 1 times 2 minus 2 times 1 and equal to 0. And yeah, here is a bit of a spoiler, so go back to this example. So here case where A is singular, and sorry, is a case where determinant of A is 0 and A is also singular, because you think about A is equal to B as a linear system. You have x1 plus 2x2 equal to b1, x1 plus 2x2 equal to b2, and this thing will never have a unique solution, because either b1 equal to b2, then solution, and if b1 don't equal to b2, then you have no solution. Okay, so this thing won't have a unique solution. Or another way to see this is if you go back to easier case of 1.5.2, we have ax equal to 0. Then this will have both equation being x1 plus 2x2 equal to 0. And yeah, this thing will have infinitely many solutions. Okay, so yeah, determinant equal to 0 if only A is singular. Okay, and now we go to calculate, go to the definition of determinant. And this is something, I'm not sure you learned this in high school, because from what I remember in high school, we only do determinant for 2x2 and a 3x3 matrix. But anyway, here is the definition of determinant for general square matrix, n by n matrix. And this is a quite long definition. We have recursive definition here. Okay, and yeah, and it's quite well, it's quite a computer science like definition here. So we have a determinant of A. It's as we say, it's a number, and we define this recursively or inductively as follows. Okay, so we say determinant of A is well, we have if A is an n by 1 matrix, then it's just A11. Okay. It's just whatever element you have, and if n is bigger than 1, then it's recursively defined, where it's a summation of this A11 times okay, now this is a bit of, oh sorry, okay, now we have a bit of I guess the base notation. Okay, so we have this big A11, but it's not element. Okay, so I guess to make it not so confusing, let's put some here. Okay, we'll think about how to change the notation more. Okay, so this big A11 is let's see. Yeah, we'll think about notation later. Okay, but anyway, this is a cofactor, and this is also a number, but it's a kind of a question we have as a matrix element. But yeah, so I guess here we have a conflict of the notation with the book. But anyway, those A1J here define is a number, and it's -1 to the 1 plus J times the determinant of minor matrix Mij. Okay. So I guess here we can have yeah. Anyway, yeah. And so this is a number, and it's defined with determinant of another matrix. And so to know this definition, we should look at here. Okay, so we have all those Aij here, and we can define the minor of the, sorry, so we have two definitions here, I think. Okay, so we have those submatrix related to each element. Okay, so for example, if A is A1J, so if on first column here, and so we look at each element, and so we just cross out everything that has the same row in the column of those on A, and the remaining part is this Mij submatrix. Okay, so this Mij submatrix. Okay, and I guess to make a notation a little nicer, so those minor Mij is put a bar on top to make it different from sub-element. Okay, anyway, so we have those Mij is defined as this matrix that's related to the ij element. And then if Aij is like here, then we cross out those parts, and we combine together those parts into Mij. And we can also define this for the middle part. If Aij is in the middle part, then we can piece together those 4 blocks together as a matrix, and this will be the Mij. Okay, so this is how we define Mij, and now we can go back to look at this recursive relation. So we have those Aij is a number, and okay. Those Aij is a number, and it's -1 to the ij times the determinant of Mij. So you can see this is a recursive definition. So determinant of A is a summation over those Aij on first column times this big Aij, which you need to calculate the determinant of Mij. Okay, and so Aij is n by n matrix, and Mij, as we say, is n-1 by n-1 matrix that's obtained by A by deleting the rows and columns containing Aij. Okay. And the determinant of Mij is called the minor of Aij. And we also define cofactor of Aij is -1 to the ij times this minor of Aij, and so we have a lot of them. You see that the minor of the cofactor are really similar thing. The cofactor is just the minor times some -1. Okay. And let's see this really cumbersome example. Definition is an example. So we go back to our 2x2 example. We have that A equal to A11, A12, A21, and A22. And we know determinant of A equal to okay, and we do this and we know from high school determinant of A is A11 times A22 minus A12 and times A21. Okay, and then we see how this can be treated as this cofactor expansion over determinant of A on first row. So it's so we had A11, then we want to have it multiply on is A22 is just the cofactor of A11 because no, we let's write this here. So Aij equal to -1 to the I plus j, and the determinant of Mij. Okay, so for ij equal to 1, 1, Mij is just this A22, and so determinant of A22 is just A22, and -1 to the ij is I and j both 1, so it's 1. And then we have A12, and then we have the minor being this A12 here. So I guess here we should say we are we expand on first row. Okay, sorry, and so the definition we have expand on first row. So we have A minor will be this A21, so determinant is just A21. Then we have -1 to the I plus j is -1 here, because it's -1 over 1 plus 2 equal to 3, and so that's how we get this -1. And so we have a very troublesome calculation to see that this definition satisfies our recursive definition of determinant. Okay, and stop here, and we will talk more about determinant on next Monday. Okay.啊？哦，对哦，哎，所以是下课时间是50分到10分这样子。哦，他们要换教室表演。哦，抱歉。抱歉。sorry， excuse me。我们有 Do we have a homework question typed out or
写题。
你都写题哦，所以没有改数字这样。那也没关系吧。Yeah, I think you probably need a book, yeah. So we didn't post it. Yeah. Good. Yeah. Good. Let's go.